Okay, so off to chapter 3, exponents and logs. I know this was a tough unit for a lot of people, and I hope I don't make it harder for people because I keep saying that it's kind of hard. But we're going to start with a series of kind of word problems, just trying to apply the concept of what of an exponential equation is. For some reason, my document camera is not actually up, so let me try that again. Um, let's go ahead and reshare this to the dot cam. Wasn't coming up, but right off the bat, we had our first question talks about some kind of an endangered species that has 8,400 seals, and it is increasing. They've done something to maybe help the species survive, and we're going to try to come up with a nice little equation. So according to what is stated, then that means we're going to go ahead and use our annual compounding interest formula right now, where when you write that a sub 0, that would be my initial population, which in this case, in this problem, it actually tells me that the initial population of the seal is 8,450. Now, it also says it's growing at 4.25%, but remember that's a percentage, and when you plug it into the formula, the R, or rate, that you have right there should be expressed as a decimal. So we're going to have 8,450 times 1 plus 0.0425 to the t power. And that's kind of really our major story. And of course, if we want to go a little bit further with it, this would just generate what happens at any time. And so, we could actually plug that into a calculator. We could take 8,450. Let's go back in here. That'd be 8,450, 1.0425 to the x power. That kind of models the equation. In terms of a window, we could say, hey, let's take a look at what's going to happen over the span of 50 years. I guess we could maybe start at 8,000 seals and go up to 20,000 just to kind of see kind of what it looks like. And so we've got the seal population growing. Now, granted, this is a long period of time, but we could actually calculate the value of the seals and say what's going to happen in 5 years or 10 years or whatever. We could do that. But specifically, we want to know is when will the population reach 20,000? Now, there's 2 ways that we could do that. One of those ways, let me make sure that it actually hits a little bit more than 20,000. But one of those ways that we could do it is we could actually set it equal to 20,000, and we could literally just look at the graph and find out where those 2 things actually cross. So here's our seal population. Here's the desired value of 20,000 coming in a second here. And we could calculate the intersection of those 2. Remember, we just have to get sort of close, hit enter 3 times, and it says, according to this, it should be in about 20.7 years, we should reach that 20,000. Now, there's another way to do that, though, where if we set it equal to, actually it does ask for 10 years, which is funny, I was kind of looking at that. And then the other one is if you set it equal to 20,000, one way to do that is through graphing it. Another way to do that, though, is to go ahead and divide the 8,450 to the other side. And then if you ever have an exponent that is a variable, we could take the log of both sides. And I kind of gravitate towards natural logs. So I took the natural log knowing that the exponent can pop in front. And so all I really have to do is divide these 2 numbers, take the natural log of 2.36, divide it by the natural log of 1.04, and we get, notice, the same exact answer that we got when we did it through a look at the graphing. Now, we have a capacitor now. Now, in electronics, a capacitor is like a little miniature battery that kind of charges up and can shoot its energy out through a system at a moment. So the capacitor decays at 17% every second. So it decays, it's going down continuously. Now, the word continuously is supposed to be kind of a fancy word that kind of tells you something. That should tell you that our problem is going to deal with E in some ways. So our story here is the amount that we have is A0E to the RT. So as soon as it says continuously, we have that. And notice that in this problem, it says initially there's 2,700 joules of electricity in there. So that A0 is going to be 2,700. It says it's decaying at 17%. So if A0 is 2,700, it tells me that R is negative 0.17. Now, I've mentioned this quite a few times. Remember, this does not have a 1 in it like this problem that we had before. That 1 right there represented 100% plus an extra 4%. When it's continuous, there's a 1 that's buried inside the number E. So anyway, without any further ado, let's go ahead and finish up that problem and then find out when there's only 200 joules left. So here we go. So I've got my formula. Notice I used a K when I did this problem, although you could have used an R. As I said, 2,700 is our initial condition, 17% is our rate of decay, and it's negative because it's going downhill, it's decreasing. Now that was actually my master formula, but then the second half of the problem says, when will it be 200? So I divided both sides by 2,700, so this would be isolated. And again, I do have a variable that's an exponent, so I want to take the log of both sides. And specifically, if we take the natural log of e to any power, it's just going to be that power. So in this case, it's pretty nice. So I have a simple decimal that I can get from my calculator, divided by negative 0.17. And I find out that in a span of about 15 seconds, that thing is going to decay down to 200 joules. Maybe for some reason, it's now safe to do something in that little situation, but that's kind of our story. Now, in number 3, we go to a population of 175. I think I gave up. I didn't even name what it was. It's decreasing at a rate of 11.6 annually. Let's just write the equation and find out what happened after 8 years. So in problem 3, we start off with 175. Notice the 1 again represents 100%. We're losing 11.6%. That's why there's a minus there. And it says, okay, so you know, that is 0.884 right there. So if we said, what happened after a span of 8 years? I just do the math and all of a sudden 175 has decreased down to 65.261, whatever population that is, be it seals or jelly donuts, it doesn't really matter. Okay, number 4, let's just try to finish up these word problems. We've got a mass that's growing continuously. Oh, here's that word again, continuously at a rate of 6.3%. Now again, this top one was decaying, this one is growing. So this one was negative, this one is positive. Again, initial condition of 27. That's what it says right here, grams. It's growing at a rate of 0.063. Write the equation and find out when it will be 50. So that's not really that big of a problem. So here we go. We've got 27e to the 0.063 t. That's my equation. I didn't have to do any work really. Now it does ask when it's going to be 50. So just like the previous question, I divided both sides by 27. Again, there's a variable in the exponent, so let's take a natural log of both sides, especially because it's base e. That's going to make that exponent happen. So in about 9.7 years, it's going to work. So I decided to pick on C-Rod, I guess, for some reason in number 5, but we're just going to say that C-Rod had some chocolate in her room. And the amount of chocolate in her room decays from 13 ounces on day 1 to 11 ounces on day 3. So what is the half-life of her chocolate? So just kind of a funny little question. So here's what we know. We had an initial condition of 13. I do not know what the rate of decay is, but I know that in a span of 2 days, because it was day 1 to day 3, in 2 days, it decayed down to 11 grams. So you know, just like the previous problem, if I were to divide both sides by 13, it is now isolated. I can take a quick log and divide, and I just found out that it's decaying at a rate. Obviously, it was 13 grams. Now it's 11. It's going downhill. So we're losing about 8% per day. Now, when it asks for its half-life, keep in mind that we had 13, so that means I'm just going to ask how long will it take for 13 to go down to 6.5. Now, these problems are kind of repetitive because we went through those steps. Again, look at that. I got a variable in the exponent. So the first thing I'll do is divide both sides by 13. and I get a half, which shouldn't surprise us. We're talking half-life, that's half of it left. Let's take the log of both sides and divide. And so, hey, half of the chocolate is going to be there in 8.29 days, which means only a quarter of them will be there after about 16.5 days. And so that's kind of the end. That's kind of a long stretch of word problems, but I think that should kind of fill that out. And so we'll do kind of the quicker problems on the next set. So that's our word problems, and we're done with those.